All right, what's up everyone? Welcome to week 89, building my own operating system. And today we are looking at some more Limine and bootloader stuff. So that's what we worked on yesterday. Ported the OS to use Limine bootloader, which changed a lot of things. Now the OS is 64-bit OS because the Limine boot protocol requires that. And today I want to learn more about what this means. There's a lot of things I still don't understand about Limine, and that's what I plan to do today, just kind of learning more about Limine, understanding better the state it leaves an OS in, specifically with virtual memory, stuff like this. I wouldn't say I have the strongest understanding of that, so that's what we're going to get into today. All right, let me just get everything set up. So how's our roadmap looking? So I think it's kind of changed a little bit. So we have done this now. My original plan was to, I don't know, work on serial driver, maybe some virtual memory, maybe some memory allocation, but for the moment, I still just need to strengthen my understanding of Limine. What's up, Bacon? Good morning to you too. Hope you're having a nice day. It is not sunny at all where I live. It is extremely cloudy and rainy, but that's just how it goes. What's up, Gabor? Yes, C++. C++ 23, in fact, although I personally don't really know a lot of C++ 23 features, but yes, we are using C++ in the OS. And let me just get my editor up. So far, we're not using so many of the features, but for example, my logging function, which I'm very proud of, is a user of C++ features. We have these nice modern format strings. Hey, Stefan. Yeah, thanks for watching. Appreciate you also. Yeah, so we got these logs, and in the back end, it's just backed by this library called Frig, which provides the formatting, but I've just wrapped it in my own function. And so that is maybe the only current example of using C++ features so far, but I plan to do more of this. So sunny where I am, 50s, starting to warm up, nice. All right. So yeah, like I was saying, maybe let's just boot the OS and sort of watch that. But like I was saying, today's plan is I want to strengthen my understanding of the Limine boot protocol, which we ported to yesterday, and I want to have a stronger understanding of the virtual memory layout that we receive from Limine. And so this is going to be more of like an experimental kind of playing around kind of stream probably. But this is what the OS looks like so far. It's kind of empty, not really doing very much, but it is using a couple of these features of the Limine protocol where we can query the address that the kernel gets loaded at. So that's the vert base, I believe. And then we can also query this thing called the HHDM, which stands for higher half direct map. And that part is a little bit mysterious to me. And so that's what I would like to learn about more. And this is all documented for the most part in this document, the Limine boot protocol. Okay, so that is the plan. I will just get started with making a branch. Mine play. And I just will commit this. Oops. Set up. This was just something I noticed. Yeah, the LLVM utilities are not in my path by default. I just get them from Homebrew, and it does not install them into your path because they can potentially conflict with the systems ones because it installs Clang and stuff like this. But I need things like readelf. At least that's extremely useful to have available. So, okay. Anything else before we get going? Maybe we'll just clean up some of these tabs. Kind of a messy situation. Let's get back to kmain.cpp. And I'll just set up my Miro board. So today is the 89th stream, and we are on October 12th. So topic of today, Limine bootloader, understand the virtual memory layout. What is the HHDM? It's a question. Try the memory map feature. So Limine has this feature where you can request a memory map. And this sounds very useful. You know what, I will also maybe open my Limine. Maybe I'll just locally clone this repo. I don't know if it's like a little bit annoying to have this in the web browser all the time. What's up, Windows 1.0? Nice to see you. Hope you're doing well. All right, I'm gonna clone the Limine protocol. Repo. I'm gonna not trust the author, no offense. And yeah, what's up, Hex7FF? Greetings. Zardis, what's up? Cock. Okay. So I'm just gonna have this around, I don't know. Zardis, I do not code in Rust. I would like to, but I just don't really know Rust, and I don't really feel like learning it right now, so yeah. Oh, we got some good avatars in the chat. Okay, so it's actually great that Windows 1.0 is here because they're very experienced with Limine bootloader. Excuse me. Also, get the break timer running. So, yeah, what are my questions? That I want to understand the virtual memory layout that the OS receives. I want to learn more about the HHDM and try the memory map feature. So concretely, maybe just pretty dumping the page tables. Preparing for master thesis defense, crazy. What's up, Geronimo? Thank you. Consistent, methodic. Appreciate that. Every Sunday, like clockwork. Except for when I am not here. But yeah, and what's up, digitalized? Yeah, kind of more for booting. I mean, more focused on specifically Limine. Right. Okay, so Windows 1.0. Useless in the chat also. What up, useless? Yeah, okay. HHDM lets you access physical memory without mapping it. Just add the HHDM value to physical address and you got the valid virtual address. So I understand conceptually what that is. It's just like a mapping of physical memory. Maybe you can help me understand. One specific question I had was, how big is the HHDM? And the reason I am asking, and my guy, week one, cheers artist. Yeah, it's a journey for sure, but I appreciate you being around. Not a lot of people have stuck around all this time. All right, the reason I'm a little bit wondering how big the HHDM is because of this diagram. Is because it says 4 gigabytes. So basically my understanding is that it maps all of physical memory. And so that's a question. That's what I believe it does. That's what people have told me. It maps all of physical memory. So if I change the amount of memory in my VM or in the emulator, the HHDM should expand maybe. And then Windows is saying HHDM is as big as the highest memory address in the memory map. And so apparently, if I'm understanding that right, the memory map is what informs you about this. So maybe I'll just start answering my own questions. What is the HHDM? It is a linear mapping or map of physical memory. These are just terms that are used by other people in like Linux kernel calls it the linear mapping. Some people call it the FISMAP. Does it lazily allocate? It seems like a lot of extra metadata if not. That's a good question, and I don't know. There's no way it can lazily allocate it because that would require like page faulting or something, and that should be under control of the OS. So I believe Limine just needs to Limine just bakes these page tables before handing off to the OS, and it literally creates page tables for all of physical memory, I think. We can explore. HHDM size depends on the memory map that we got. So it seems like the memory map is an obvious place to just start doing things. And that was sort of, well, I was also considering dumping the page tables just to see what they look like, but maybe the first thing we'll do is just try out the memory map feature. So let's do that. I don't really know how to do that, but let's check this out. Memory map? Okay. Yo, what's up, V-Pool? Nice to see you again. Thanks for coming to all these streams lately. You've been in a lot of them. And I wish I preview Markdown, open to the side. Okay, so let's parse the memory map or something. So I'm going to, wait, what is this? This is the CXX template, which we don't really need right now. All right, I'm just gonna add a function that's called memory map play. I'll just do that here, memory play. Oh shit. Do I accept the AI suggestion? I was like kind of looking forward to writing the code myself. Maybe I will just keep that, but then keep it commented out for reference, and maybe I will turn off code completions. Okay, so make some more space. So first step is I'm going to go to my limine.hpp, and I'm going to add the request. And so let me see if I remember how to do this. So I'm going to make a HHDM memory memmap request. Limine memmap request. All right, bet. And then is there actually anything else I need to do? I just like, so I add the request, and then what? And then okay, I think this was correct, but so the way you use these limines, let me check the chat. Yeah, okay. So the way you use the feature is basically, I have this global Limine requests object, which is this struct containing the actual requests. And then Limine populates those requests at load time. So then the kernel does not need to do any parsing at all. It literally just starts to use these objects, or these structs. And so I don't know. This actually looks kind of right. So, but I need to name it mem map. Okay. So now honestly, you know, I'm going to delete this code. It's this very distracting for it to be here, and I will stash it far away in Miro in case I really get stuck, but I did not want that actually. Okay, so now let's check out. So we get the memory map and we put in the request, and the response contains lists like a double pointer to some entries and an entry count. So we can just, I don't know. This is a little bit, oh shit. Auto response. But okay, no, I will keep it as pointer response. Okay. If okay. So now we have the response. So okay, I'm just gonna start with that. Nothing too complicated. Let's see how many entries. We got 16 entries in the memory map. So So now a pointer to an array of entry count pointers to some of these structures. And this VS Code is a little bit janky. Okay, so maybe I can just dump okay. So there's different ways I could go about doing this, but maybe I'll just do it in the simplest way. So we get a pointer to an array of pointers. Okay. I'm just gonna go for it. Equals P response entry count. Hey, wall markets. What's the name of my OS? I have not named it. The folder is called JOS still because I never renamed it and we were working with the JOS OS. Wait, what am I doing? I is less than, okay, plus plus. Okay, and what are we doing here? We are going to get the P response. It's not just JOS, not just. I named it unnamed, good. Entries, P entry. So we're looping through this array and each of the elements in the array is a pointer. This should be struct mmap entry. And we should even be able to, oops, sorry. We should even be able to dereference this thing, right? These pointers should not be null, right? So we could even go as far as, we could assert p entry or something like that. Tree. Do. Okay, nice. For 100, from how much you done for 1.0 V? Honestly, dude, I have no idea. I don't really think in terms of that, at least not quite yet. Like 100% or whatever. So now we have an entry and we can do what? We can dump the entry. So let's just do that. Entry entry number 1. Also, what's up, NSG? Yeah, I don't know. Does it hurt? Does it hurt having an assert here? I feel like that's the whole point of asserts, actually. The things that should never be true, that's what you assert, just to really make sure, because who knows? Okay, base, length, and type. So maybe I'll just do it like this. Base, length, type. Entry.base, entry.length, entry.type. All right. First time dumping the memory map. And I need to make these hex. Why not? Why not? I'll make them all hex. All right. Just gonna take a picture of this. I don't know. Don't really know what I'm looking at just yet, but it's something. All right. Base, length, and type. So let me read a little bit more about what this means. Okay, so or maybe it's documented. Okay, time to read. So we have some types. There's different types of memory regions, and we get a type. Yo, what's up, Afnan? The Lord. Definitely not. Definitely not the Lord. but we are dumping some memory maps, so that's cool. Nice to see you. Okay, and then what's up with the base? Okay, so basically, base. This is looking so I'm going to kind of guess that this is like a physical offset. Like we're talking about the physical memory map, right? So we're on revision 3. And this is kind of important. I feel like it's good to know. The HHDM is a linear mapping of physical memory, but not all of physical memory. A selective mapping of the useful parts of physical memory, I'm going to guess. Like this, so I'm just gonna snag that. All right. Usable, bootloader, reclaimable. Now that is something I don't totally understand yet. I mean, I have a sense of what it means, but we are ready for the first break, so I'll be right back in 20 seconds. Okay. Bootloader reclaimable. This was used in other places. Or maybe not. Why do... I'm just wondering about things like the page tables. Yeah, I feel like I saw somewhere, so I'm wondering about where the page tables are stored. Because Limine allocates page tables, obviously. Right. Oh, there's the dash here, which is why I didn't get. Just the bootloader are in bootloader reclaimable memory. And their specific layout is undefined as long as they provide the above mappings. So that's interesting. What's up, Ismail? Learning a bit about memory layout and how Limine does things. So my question is what is the consequence of something being in bootloader reclaimable memory? Is it okay to just like rely on things there? Or do I need to like migrate, I don't know, the page tables out of that memory or something like that? That is my question. What is, what does bootloader reclaimable mean? Like, okay, the bootloader can reclaim it evidently, but like when and like how? When, how, why might the memory be reclaimed? Can the kernel rely on things stored in this memory, or is it just for the initial boot handoff and the kernel should migrate to its own page tables, etc.? I mean, the answer is probably yes. Like, that's, I would guess. Otherwise, otherwise the kernel is just going to forever be working with these random Limine page tables, I think, if I'm getting that right. And that doesn't really sound like the right way to do things. So sort of don't understand that, but maybe I won't get caught up in that for now. Okay, maybe here's the part, maybe it's time to you're expected to set up your own page tables. It's safe to use the usable entries only. That makes sense. Okay. NSG says safe to use usable entries only. Need to set up own page tables. Okay, so basically we have a certain memory layout with the kernel being loaded somewhere and a linear mapping somewhere else, but we can kind of do whatever we want. Limine fetches it from the EH20 on BIOS and the EFI map under UEFI. Interesting. Okay. So I'm just going to learn a little bit more about what these mean, though. So we have a map of a bunch of different sections of memory, physical memory. Nothing's at like 0. Okay. And then I was just sort of thinking it might be nice to have a pretty printed type here. Just as an exercise, how I don't really want to write that code myself, so I'm gonna try to prompt AI to do it. Star entry type to string, something dumb like this, and we're going to take a UInt64T type Let's go. So this looks pretty good. That was pretty sick. I gotta admit, that was pretty cool. Except I cannot, why can I not jump to definition here? mmap, usable, reserved. Executable and modules. Executable. All right, so we got our AI generated helper, and now I'm just going to, should we type to string, oops, tree.type. All right, this is like not the easiest to read, but that is kind of nice. So we have some bootloader reclaimable memory, very low, and it is for like hex 51 pages. And then hex 52,000, we got a bit of usable memory, got some reserved memory, some more reserved memory. And then at the 1 megabyte mark, I'm just going to take a screenshot of this too. All right. Experimented Gabor. VMware interesting maps appeared. Somehow the full memory was never available. Interesting. Yo, what up, Tugra? I see you. Okay. Then we jump. Then we have a large region. You know what? I want to pad this. You know, we're using all this like fancy formatting library. Please pad the base and length here to 64 bits. Or I could just ask ChatGPT how to do that, but hex 16. All right. Let's try that. Again, just to make this hopefully a bit easier to read. Nice. I'm just gonna pad. Is this how you pad things, Hex? I'm just gonna try it. All right, check that out. Now, perfect alignment. Work of art. Memory map belongs in a museum. Okay, that's a bit easier to read, right? So we got a large section right here. And then we jump over into a bit higher, and some other random stuff is there. We have a relatively small chunk of randomly usable memory, another section of bootloader reclaimable, reserve. Okay, cool. So really we only, okay, so this so really we have 3 segments of usable memory, and it's mostly in this one. And let's just jump back to over here. Wait, so anyway, so this thing is saying for base revision 3, only memory map regions are these 4 things. And then is that that seems to be consistent. Interesting that the frame buffer is around, even though we did not request it, but whatever. So we don't get reserved. Wait a sec, what? I'm confused. We're getting a bunch of these reserved. Oh wait, okay, so wait, this is the complete memory map. But just because something is in the memory map does not mean it's mapped into the HHDM. The memory map just lays out, okay, like what is there in physical memory? Then the HHDM maps a subset of these entries into the HHDM base, which is right here. So basically, if we need to access the physical memory, we can just do that by doing offsets against the HHDM base. But it's not supported out of the box to do accesses into the reserved or bad memory. Because I guess the thinking from the Limine authors is like, why would you do that? You like should not do that. So it's just not supported to do that. It's safe to use usable and bootloader reclaimable in NSG. Oh, okay. But that's sort of the part I don't really understand. This bootloader reclaimable memory has a very scary sounding name. It sounds like at any point the bootloader can take that memory back or something like that, which doesn't make any sense at all, because as soon as the OS starts, Limine is not really active anymore at all. It has completely handed control over. So in that line of thinking, it actually does support what you say, where like actually the bootloader reclaimable memory does sound completely safe to use. In which case I just don't. Oh wait. You can, okay, I think I see what it means. It's not that the bootloader is going to like take it away, it's that the OS can reuse that memory. Also, what's up, Elo Below? I think that makes sense to me now. I'm gonna take a note of that actually. So, so NSG says safe to use, usable entries, and bootloader reclaimable. Okay, so the answer is that this is memory used by the bootloader to pass for page tables and other and response. Okay, page specifically, it's page tables, response structures, and the stack, because Limine also creates a stack for you apparently. So initial stack, and is available to be reclaimed by the OS after these are no longer in active use. Okay, thank you for helping me clear that up. Okay, so what I'm taking away from this is actually, it is basically just safe to keep using these initial page tables for an indefinite amount of time, and I can build upon them and mutate them at will to actually construct the production virtual memory layout that I want to have for the kernel. And concretely, the page, like the page, like the PML4 table or whatever, like the highest level page table is just created by Limine, and that might just stay exactly where it is for the entire lifetime of the OS. Okay. So time to just do another experiment maybe. I am curious what it looks like to greatly expand the physical memory of my VM, and I just want to observe a change here. So, but I'll just stage these things. I mean this, yeah, whatever. I'll just stage these things for now. Oh man, am I pronouncing this wrong? Limine? Dang, thank you for the correction. That's embarrassing. Limine bootloader. Okay, thank you. Okay, so let's just do a quick test. Let's just jump to the tool chain. And actually, I'm just gonna move DevTools. I'm gonna move this line up here actually. And I guess GDB. What happened? I'm just gonna. These dev tools. I'm just gonna move all these things. Okay. It's not advisable to use the existing page tables, just build new ones according to the memory map set up by Limine on startup. It's not advisable. Why is it not advisable? Because it sort of seems to me like if I understand bootloader reclaimable memory, it basically just turns into just valid kernel memory that's like usable actually. So I would be interested to learn more about that. What's up, Mikhail? Nice to see you too. Thanks for joining. Okay, so since existing yeah, okay, I guess I see it. So if the idea is that we just fully reclaim all of the bootloader reclaimable memory, then we will clobber our page tables. Yeah, right. So maybe it is. Okay, that does make sense to me. Like, there's a couple different scenarios here, I guess. So in the simplest case where we just don't take advantage of the bootloader reclaimable memory, then seems to me like it is safe to just kind of leave it as is. But we'll leave some memory on the table there that's wasted. And so we could try to reclaim it, but then if our page tables are living there, we need to be careful to not like disrupt them basically. And maybe that's kind of tricky. So maybe a safer thing that NSG is saying is we migrate the page tables out of the bootloader reclaimable memory into quote unquote normal kernel memory. And then that will make it easier to do a full simple reclaim after the fact and not require like being very careful to not disrupt the page table. So I do see the point there. That makes sense. So it's not a great idea to leave to continue using the initial page tables in bootloader reclaimable. Not move out, just build a new one matching. But they, but the new one needs to be somewhere else, right? It needs to be located in the usable region, if I'm getting it right. So you basically okay, I'm thinking like you would need to do kind of like a deep copy of all of them. Like for any of the page tables or paging table structures that are in bootloader reclaimable memory, you need to allocate a page in the normal memory and then like mem copy it over, and then probably fix up the pointers. Maybe I'm overthinking it, but that's sort of how I'm understanding. If it really is sort of like undesirable to like leave things in bootloader reclaimable memory, that's sort of the way I'm thinking you would need to go about doing it. Maybe I'm wrong. If you ever wanted to fully reclaim all that memory, you would need to be very careful to not disrupt page tables living there. So perhaps need to migrate them out of that region. Which will make it simpler to reclaim the BR memory. Something like that. All right, feel free to join me for a quick stand up and stretch. Okay. So I wanted to do an experiment, and I will just quickly stage these changes. But the experiment is I just want to add way more memory to Kimu, and there was some flag for this or something like that. It's the -m flag, okay. Dash lowercase m. So let's boost it up to 1 GB memory, just for fun, and then I don't know, we'll see a difference maybe. So I think here's the difference. Let's say the same. 4D, this big thing, 1F, and that's really it. That's like the only usable chunks. 4D, 1F. So it's really really just this one very large section. Yep. And then that actually offsets everything else. Page allocator time. I guess so, maybe, yeah. So now I think I understand the HHDM well enough. It's basically just a linear mapping that exposes these 4 parts of the memory map. And I guess the purpose of the HDM is it's useful for accessing physical memory at this early point in the kernel. But when we migrate and move over to, I mean, we don't necessarily need to keep the same virtual memory layout that Limine passed to us, but maybe that is actually just a very simple thing to do. And just keep the same idea of an HHDM around at the same address even, and even keep the kernel virtually loaded at the same. I mean, I think actually the kernel kind of needs to be, because the kernel is specifically linked to run at this address. So while we do have some freedom to potentially change the virtual memory layout, that is one thing that I think cannot be changed, really. But the HHDM, for example, that is open to different ways of doing it, potentially. It doesn't need to be at this address. But this is probably a really good address to do it at, although, because it's at the starting point of the top half of the 64-bit address space, which is completely non-obvious from like looking at this address, but that's my understanding, I think, of how it works on 64-bit x86, where you only have 48 bits that are used, and there's this notion of like the lower half and then the higher half of the 64-bit address space, and I believe this is the bottom address, like the starting point of the higher half. So that actually does seem like a good place, if any, to leave it. All right. So I guess what would be the plan from here? So NSG is saying page allocator, and that probably makes sense, because let's say we wanted to do this page table migration thing. If I'm getting it right, to migrate the page tables, we're going to need, oh yeah, try running with CPU Human64 LA57. That's going to change it, right? That's going to enable 57 bits or whatever of virtual address space, right? All right, I'm going to not do that for right now. I'm going to stick to my simple 48-bit world. So let's maybe map out a bit of a roadmap. And so initial Limine, that's already done. Learn about virtual memory layout, memory map, and HDM. That's also officially finished as of like right now. So now what is in our future? So some idea of migrate to kernel, I'm going to call them the production page tables owned by the kernel in usable memory region. And for the reason that we were talking about earlier here, and I mean, yes, that's mainly the reason. And if I'm understanding it right, in order to do that, we're going to need the page allocator. That's kind of like a prerequisite, because we're going to need to be able to allocate pages, like physical frames, basically, from the, well, I guess we'll start with the usable region if we want to get really fancy with it later, we can add a way to like kind of add a switch to the page allocator, and at a certain point we flip the switch on, which releases all the bootloader reclaimable regions and allows them to participate in as like a memory source. But for the initial part of the page allocator, it will ignore the bootloader reclaimable region. So, so I think NSG is right, is that that does make sense as a next step here. I'm just trying to think if there's anything else I want to do before I dive into that project. So that was fun to add a gigabyte of memory, but I'm just going to remove that. I'm completely fine to live with 256 megabytes for the moment. Okay, now just to check, does my debugging still work? BK. Did it? Oh, did it? Oops, no. Let me try that one more time. BK main, continue. There we go. Okay, so that is still, I'm just want to make sure because I moved these constants, but it seems like move debug kimu bars into dev tools. Let's see, make a bit of a cleanup commit. This random thing, I think I'll just stage these as a whip for now. How do I like Limine so far? I like Limine, or sorry, Limine as Limine bootloader. I like it a lot. The documentation is really good, and it's definitely true that it provides a lot of services to make it very easy to get started quickly. And I do have to say the way the Limine protocol works in terms of these requests and responses is extremely convenient from the developer's point of view. With like multi-boot and multi-boot 2, it required like you need to like kind of parse this blob of memory and like parse this data structure, like these data structures out, and you do way less of that with Limine. You literally just like have these objects that you declare in your program, and then Limine goes into it and populates some pointers in them, and then after it does that, and then it loads your kernel, you just literally use these objects that you've allocated. So that's really nice, to be honest. That's very convenient and very easy to use. And this memory map seems pretty good. The HHDM is a nice, just a lot of conveniences. Like it makes the stack already. There's no assembly needed even. I think that's very interesting because I think a lot of people assume, at least I was assuming, that the OS needs to have at least a little bit of entry-level assembly, like entry assembly at the very start. But Limine shows that it's not necessarily a hard requirement for an OS to have assembly at the start of the boot process. But it's just a bit of a matter of taste, I guess, because Limine goes through a lot. Limine is very opinionated, and so it just basically includes that entry-level assembly that you might include in the OS. It just puts that in the bootloader, and maybe there are some trade-offs there. But so far, I do like it a lot. and it's cool to be on 64-bit now too. So yeah, that's my review of Limine bootloader. I think it's worth, lives up to the hype. Okay, so let's just quickly touch on these regions, because I mean, maybe, you know, I was speaking a lot. A lot of this stuff is actually documented. So that are usable RAM do not contain random stuff, so they're for use. Reserved. ACPI reclaimable. So I guess similar to the bootloader reclaimable. You can maybe reclaim them. We don't have them right now, as far as I know. Bad memory, so don't use that. In Kimu, we do not have any bad memory. Okay, containing RAM storing bootloader from it should be available to the executable, meaning the kernel. MB trampolines. The executable should make sure that no data is needed. Okay, make absolutely sure before reclaiming them. Oh no, this is actually interesting. So this executable and modules, this is, wait a sec. Okay, I straight up do not even see that here. Oh wait, I'm blind. Executable modules. So this is where a kernel gets loaded in physical memory. This kind of goes back to that thing we were talking about last week, where Limine ignores the physical address fields in the elf load segments. So normally an elf loader loads the elf based off of the metadata in these load segments. And I would sort of assume that for an OS loader, it would also respect these, but Limine actually does not respect them. It ignores the physical address fields, and it decides on its own accord where to load the kernel in physical memory. And it is loaded into basically an unspecified place. And this is where it is. Elo saying physical address doesn't matter. Yeah, I guess I would probably agree with that. But I don't know. Yeah, maybe there are some reasons why you might care about that. I don't know. And if you actually did care, then you would not be able to use Limine. But for most people, it probably makes sense that you don't really care about the physical address. So here's where it is. It's sort of like we have this large section of usable memory, and then just like a bunch of other random stuff after it. It's sort of interesting why there's like these holes there. Like, why is there this random hole of usable memory and then more bootloader reclaimable memory? Like, why not? Why wasn't, I don't know. Anyway, whatever. Yeah. What's up, Anthony? Why C++ and not C? I don't really know C very well, and I also I really like the features you get with C++, so that's why. Okay. Frame buffer. These entries exist for illustrative purposes only and are not to be used. What does that mean? Okay. I'm not using the frame buffer, so I don't really care, but this phrasing is kind of interesting. What kind of illustrative purpose? Okay. For base revisions less than 2 is never marked as usable, but apparently from 3 up it might be. Guaranteed to be sorted. Guaranteed to be aligned on 4K. Usable are guaranteed to not overlap. Are not guaranteed. Wait, what? Okay, so these are guaranteed to not overlap, but all of the other random ones, including executables and modules, this is interesting, they have no guarantees about alignment nor overlap. So that is very interesting. Basically saying, like, don't touch them or be very careful when you do. Interesting. Okay. Alignment and overlap and non-overlap guarantees for usable BR, no guarantees for the other non-usable regions, including executable and modules, which is interesting. Okay. Then yeah, there are all these other performance features, date at boot. There's all these other features. We are already using the HHDM stack size feature. You can, customize your stack or something? You can request a specific stack size for the entry stack. That's interesting. Firmware type, you can query on what kind of firmware things are booted from. We're using the command line bootloader info. All right, feel free to join me for a quick 20-second stand up and stretch. Okay. Anything else? Machine. Okay. So that's basically it. Bootloader. Name and version of the bootloader. Okay. The requested entry point. That's kind of interesting. So I'm going to assume that by default, it uses the entry point in the elf. But apparently, if you want, you can override that or something. So let's go file. pointer to this file structure so you can get information about your own executable file. How do I see this? So you can get some string, oops, media type, unused. Okay, some random stuff in there. File structure, what is? Oh wait, this is just, this is literally what we just looked at. Always at least for. Okay, some path, other random stuff, okay. Date at boot, get some boot time info. Okay, nothing really mind-blowing, and I'm already using this. Okay, so I feel like I have a relatively good grasp over what the different features are of the boot protocol. And yeah, I guess now, yeah, working on the page allocator sounds like a reasonable thing to do. And yeah, I'm coming at it very much from first principles. I have the idea, I know how JOS's works, but yeah. Okay, but yeah, so what's the idea with the page allocator? So we just have all these raw areas of physical memory, and we want something that kind of abstracts over that, because it's kind of messy. There's all these holes and stuff. So page allocator. So there's all these holes, and ideally we would be able to use all these regions of memory, and we want to kind of layer over this and abstract over that messiness with some kind of abstraction that lets us query for page size blocks of memory, aligned page size blocks of memory, basically. And yeah, and we should be able to free them too. And so that's all pretty standard stuff, I guess. And so there are different ways you can implement this. And the classic techniques are like the free list technique, which is what JOS uses. It's also the bitmap allocator, which is maybe kind of an interesting idea. And those are the two main ones I'm going to consider. So the idea with the free list, buddy allocator. So So to be honest, I'm a little bit less familiar with the buddy allocator. I have a loose understanding of like you have this big region of memory, and then you progressively cut it in half or something like that to satisfy allocations. And that's sort of all I know about it. I did not know that's what Linux uses, so I'll write that down. I think my goal right now is to do this as brutally simply as possible. Apparently Linux page allocator. Okay, so I think I'm just gonna try to start off. I mean, I'm also gonna, like go from, like, what is the worst page allocator I can imagine? The worst page allocator I can imagine doesn't even really handle like different chunks. You basically just give it one chunk and that's it. And so that's like the worst one that I can imagine. Maybe that's like a good starting point. And in this case, we would basically just be using this middle usable region as the place where allocations come from. And then there's different iterations where we can get more and more sophisticated with it, like actually supporting these different chunks that are non-contiguous. Maybe that's one reason. So what are the different levels here? Worst, best. So probably the worst idea, ignore the holes, simply allocate from one big contiguous chunk. Right, the worst page allocator is the freelist that links pages one by one during boot, which slows down. So I think that's worst in a slightly different way than I'm talking about here. That's sort of like a specific implementation technique. I'm thinking more in terms of like high level structure of what facilities the page allocator even provides. And so maybe the double worst one is one that doesn't handle the holes. It only handles like one chunk of contiguous RAM that you give it, and it does like the slow free list thing that you're talking about. I'm more focused on the high level aspects in order to like help me break down the problem. And my plan is just kind of incrementally work through it. And so my worst high level design is, okay, ignore the holes, simply allocate from one big contiguous chunk, and then you can level up a little bit, handle the holes, and then you can get really fancy and allow bootloader reclaimable regions to be allocated from at a specific point in time. Handle the holes. Okay, so allocating from multiple non-contiguous regions in the memory map. Yeah, absolutely. Yeah, right. So it's totally possible that there is now a big chunk. For the purposes of iterative development, I do have one right now, and so I could get started with that. And then, of course, you would never you would not really want to use this one. But then that's a good stepping stone to the next one. So I think I might just start with that. Yo, what's up, Tyson? Yeah, you're welcome to join us. Please do. All right, and then so I do have some experience with the free list, so that's what NSG was saying. One secret trick I have up my sleeve is also the idea of the ETL pool, which is a data structure available in ETL, which is this library that I have included. And it actually sort of implements a free list allocator. That's sort of like what it does, except it does it in a bit more efficient way. So it does not link the free list immediately all on construction. It uses this like lazy free list technique. So I'm kind of interested in doing it that way. But let me just, I'm just gonna pull up the old JOS code just to help me kind of get like a reference to this. So I'm pulling up my code JOS 2. This work? Okay, here we go. So just to help me orient a little bit, the way the JOS allocator works is it's in pmap.c, I think, and page init. Okay. Damn, we got 28 people in the chat right now. Holy, I wasn't even looking at the stats. This is like way more than I've had in a very long time. What's up, Daylight? No, this is okay. It's like kind of complicated, but sort of. So it's like kind of from scratch. This OS, this like untitled OS. I am using a bunch of third-party libraries, to be clear. But it's like kind of from scratch. And historically, I was working on this other OS, which was not from scratch, which is called JOS. And I do reference it quite a bit. So here's JOS's physical memory allocator. It's like kind of poorly implemented, like kind of like messy because I did it that way. But basically, we have a couple of things. So we have number one, we have this big array of these page info structures, and each of these represents basically a physical page. And this is a seriously like long list of page info structures, and basically they're linked together in an intrusive list, like an intrusive free list. So it uses the free list technique, and that's what happens here in this page init function, which is what Elo was talking about. Is super slow apparently, or whatever, because you like iterate through this like super long list to link it all up front. And you can trivially convert between a page info and its actual physical address, just by applying, like finding the offset of a page info from the start. And then the actual allocation, or just also one thing. So the one interesting thing about this function, and the one that's relevant for us right now, is all this code that excludes a bunch of stuff from the allocator. And the purpose is exactly the same as what we're trying to do right now, where we're like kind of trying to exclude things from being allocated. Or people are saying bitmap allocators, what they used. Yeah, I like that idea. And basically the way that this is implemented in JOS is it simply does not link certain things into the free list. So when we have this big array and it like goes through the array and like links things, it is selectively excluding things from this linking process. And if something is excluded, then it will basically never participate in the page allocator. So that is the way that's done for JOS. And so I don't really know what I'm doing, but I'm just going to kind of sketch it out a little bit. So I'm going to make a new file, and I don't know if page allocator is like I don't know if is that the name I want to use for this. I feel like page is kind of confusing. I'm going to call it frame allocator just because physical frame is sort of the terminology I am kind of used to for this. And I guess I'll just start sketching something out. So I'm just sort of assuming we need like a list of structs, but you know, maybe I'm even wrong. Maybe bitmap is a good strategy. What would a bitmap allocator look like here? So we have a bitmap that is expanded to the size of maximum number of pages available, basically. And then bitmap allocator. So I don't know. There is going to be some kind of bitmap that's stored here, and then we're going to have some functions like alloc and dealloc, and sized to contain the maximum number of pages available, which to start off might just be the so let's just call it the usable regions. And then in the allocation function, so it's obviously not going to return void. It's going to, but I don't know what the return type is just yet. So the allocation function does not take an argument, and I don't know, there's like takes some to free, doesn't take, and basically we need to find free frame, like a free bit in the bitmap, which is going to be a linear process. So linearly find a free bit in the bitmap, set it / mark it as used, and then return something. And it actually doesn't really matter, maybe. We could return like the physical address or something. Maybe that makes sense. And so I have this phys_adder t type, so I'll just include that, include memory. So phys_adder, so it could return the phys_adder convert bit index to phys_adder, and then return it. And again, the idea here is that it's trivial. Is that how this works? Is how do you convert between okay, so I think I see. So the bitmap will represent like all of physical memory, and then just certain chunks of the bitmap will just never be eligible to be allocated from based off of the memory map, actually. And so I sort of see what you guys are saying about this being very simple, and it's becoming a bit clearer to me. And so it's something along the lines of, for each bit in the bitmap, first check, is the bit in a usable region? If not, continue. It's just not eligible. If so, is it set marked already? If so, continue. Then if it's not marked, then it's free for use. Let's use it. Okay. This does sound pretty simple. So this does not, and I think I got a little bit confused or maybe misled by JAWS, because JAWS has this page info thing, which is used to store a ref count. And that actually does sound useful to have later. But I don't need it right now, so but you know what? I mean, the bitmap technique does not preclude doing that. What might change though is like we have the bitmap, and then we might have like a parallel array of these info structs to contain metadata, and the bitmap, like the bit index, just sort of maps like one-to-one to this other array. What's up, Desi? You could default to unusable, used being the default. Then you just check if it's free. Yeah, I mean, I sort of understand what you mean, but in my view, it's kind of... And then I'm not quite sure how this conversion would work between the bit index and the physical address. I don't know if it's helpful to try to illustrate this somehow, but the design I'm kind of thinking of is, can I make this thicker? So let's just pretend this is physical memory, including all like the random holes and like weird stuff. You know, let's all right, I'm going to kill the palm tree. Let's like pretend this is physical memory. We've got some weird holes, and I don't know, let's say it looks like this, and this one is usable, and this is usable, and then like these other random ones are not usable. So what I am thinking of is create a bitmap, and this is like relative to memory, this is like pretty short, but every bit in this bitmap corresponds to a page. and simply it just like, how do I draw an arrow? All right, simply like this corner corresponds to there. And this corner, you know, this end of the bitmap points to here. So this is not the way, Desi, you're talking about, but this is sort of the way I'm thinking about, which is very simple. And just so like, so there's going to be a lot of bits in this bitmap that correspond to unusable pages, and that's like, okay, that's the design I'm thinking of. If we were to try to do it in another way, where this is memory, but the bitmap, if I understand, Desi is suggesting a way where the bitmap points like only to the usable regions. I don't know, like then you can assume that everything here is free, but then like what, then do you have multiple bitmaps? Like I'm a little bit less clear on that. So and then the conversion between bit index and physical memory, right? That's like, that conversion is trivial if you do it like this. Each bit just corresponds to a frame here. And then in here, it's actually it's more complex. Like the mapping between what bit and what frame we're talking about is quite a bit more complex, and you need to take into account the actual memory map. So, okay, got you. Maybe maybe I totally misunderstood you. Right. And she's and she's saying how to actually decide the bitmap. You get the highest page frame number, right? And then below. So Rels too. I've talked to Andreas Kling before over the internet, but I don't know him super well. And that mem set the bitmap to all used for every usable chunk. Mark the bit as free. Interesting. So, okay, I see. That's actually kind of a smart technique. Yes, good idea. So allocator is describing a way to not have to do the check every time here. Allocator is basically saying, in the initialization of the bitmap allocator, bake that information into the bitmap ahead of time, and then you just don't need to do all this checking all the time. And that's actually a very good idea. Thank you. Okay, y'all are way ahead of me. Thanks for bearing with me as I slowly understand this. So let's try to do this. So first off, I sort of feel like I need to it would be nice to harvest the information about the memory map into, I guess we already kind of have it here, but it's basically just getting this list of entries. So really the first thing I need to do is figure out what's the maximum page frame number, like how big does the bitmap need to be, and kind of just going back here. So again, going back to the stupidest way to do this, I feel like it's probably it's something, you know, it's like base, it's like the last one. Base plus length minus, or maybe just simply that. That yields the highest physical address available, and that is also the size of the bitmap. So I'm just gonna like noobishly like try to do this. So yeah, all right, I'm just gonna code it like straight up like right here. Okay, so, or you know, I'm gonna make a function, and I'm just gonna prototype it right here. So we're going to, I don't know, find, you only care about usable maps. Last base plus length minus first base. Let's check that out. Last base plus length. True, so technically, but okay, then we need to take it, then to convert between the indices in the bitmap and physical addresses, we need to take into account that initial offset, right? And that sounds pretty trivial, true. So, but also slightly in optimization, I guess. Okay. All right, so I'm just gonna call this find, let's call this get like num phys pages, something like that. Okay, num phys pages. And I don't really know what the type is, but I'll just make it an int phys pages. And this, I guess this needs to, it's gonna maybe just take the response, Limine mmap response. Okay. Const Limine mmap response. Let's call this mmap. Yeah. Okay, and then what we were just saying is we need to get the last entry. I'm just gonna code this like very verbosely. Entries at mmap dot entry count -1. Get the last entry, and then we're in last entry dot base, y dot, right? Oh, these are pointers. Oh, yeah. Last usable, right? So theoretically that would be here. And so that that's kind of, okay, so that's kind of like an optimizing, like an optimization, basically. All like, we only need to care about these. So we could find the, yeah, I see. Interesting. But in theory, this still works. Base plus p last entry dot length. I'm just coding it kind of a bad way, and then it's the number of which is like 12 or something like that. Yeah, something like this. But then, yeah, you would be saying, actually, no, you're wrong. Like, don't get the last entry. Actually, just find the last usable one, and then get that. And use that for the bitmap size, which is probably a pretty good idea. So let's do that. And so I guess what I want to do is maybe make a function that returns, we'll call it the last usable region. And also, so given the memory map, we need to or I don't know, maybe I can make this an optional. Is it optional? And then kind of the same thing here. What is it? Map dot entry count. Oops. Map dot entries. If entry dot type equals usable, then reds equals I, something like this. Let's just test this out. So let me just read this, double check. So get our return value, and then get the optional. Text. Okay, so now I'll just do x equals last. But in order to do this, I need to have the memory map, and so realistically, it's just right. We're asserting that, and then we can just pass the Limine request.memmap dot response. All right, and then we can log last usable region index. Okay. All right. Damn, 27 people in the chat today. Active chat today. Nice. Okay, so now let's just run it, and this shit does not compile because it's an optional. Index. And okay. So time to check this. Is it right? 8. Last usable region index 8. So it looks correct to me. Word. Okay, so now that we have this function, we can then use that to basically do the same thing and last usable index. And now, instead of this last, so now we use that, and then something along the lines of this. We get the entry, and we're pretty much guaranteed that it has something, but whatever. And then we just get this number, we add the length, and then the result is basically like the first out of bounds address. Which gives us the number, and we shift that down. So anyway, to do use constant, use named, use var, not raw 12, and then we get the number of physical pages. And I don't know if int is the best choice here. So quick math, how much physical memory is that? So, dang, how do you do this again? 2 to the 31? Shit, what's in max? 2 to the 32 minus 1 is obviously uint. Yeah, I'm pretty sure this is it. And then so that What? Yeah. What is int max? I'm pretty sure that's int max. And then so it's this. Yes, that was right. Yeah. So so then that's the number times 4096 page size, right? Gives you maximum of memory. Then divide that by, let's call it megabytes or gigabytes, which is 8,000 gigabytes of memory. Did I do that right? We can store up to int max num pages. Each of those is 4096. So I'm gonna say that that's sufficient. And int for num phys pages is sufficient. Okay, so let's just print that out. And while we're at it, let's call it frames, just because frames equals num frames. And actually, yeah, okay, so let's just check this out. All right, so what's going on here? Let's just double check the math. So last usable one. So let's just manually redo the math. This plus this, right? And then we just mask that down by 3. So hex 7F81. So, right. So that is the number of frames available as the maximum possible usable number of frames. And so that is going to be the size of our bitmap. Okay. Then here's maybe the fun part. So I have access to a couple of bitmap types. There's one in there's a bit set in Frig, although yeah, the thing about these things is that they are static bit sets. So there's a bit set in Frig, and then there is the bitmap in, or is it also called a bit set? There's a bit set in ETL. And I don't even know where to find this thing, but Yeah, phrase is a little bit simpler, possibly. Let me just quickly check. So basically what, so I have a couple options here. And so one, I could implement a dynamic bit set, but that requires that kind of requires a memory allocator actually. So I think the pragmatic solution here is choose a large number for the bit set and have that be at compile time. Panic, like choose a conservative large number basically. Like I don't really want to have this, I don't even really know how I would do it without an initial memory allocator for the dynamic bitmap. So basically we're not doing a dynamic bitmap, we're going to do a static fixed size bitmap, and we're just going to need to make sure that it's big enough for what we need. No, you should find a large enough memory chunk. Yeah, so, okay, so Ilobilo is saying, to just like allocate memory from the usable maps, which is kind of funny. Like it sort of already requires allocating memory, right, though? Yeah. Yeah, yeah. Yes, there's different ways to go about this. I might just move fast with this idea for now, but let me take a note. So Desi overestimates and puts theirs on the stack. Interesting. You know, that is also another good question of where does the bitmap live? I mean, like, yeah, like, Ilobilo is saying you need to dynamically allocate this thing in the usable memory. Desi is saying, okay, I just put mine on the stack and kind of overestimated it. I'm sort of inclined to go with the latter method there. This is fun. So we're going with the bitmap method. And just to summarize the work a little bit, based on the memory map, compute the largest payphone number corresponding to the max usable region. No need to use bits to represent the end regions that are not usable. And then where does the bitmap go? Like allocate mem from the usable mem for it. How? We don't even have a page allocator yet. So maybe we just need to specially reserve a page or something like that. Yeah, sorry, Ilobilo. I think there are issues with sending links in the chat, unfortunately. But if you break up the link, that should work. I've looked into a lot of settings for this and I don't know how to fix this, unfortunately. Sorry. Okay, so number one, we also can simply overestimate it and put and allocate it statically on the stack, on the data segment potentially is the global variable. I think I will just proceed a bit with the overestimation number. So based off of experimental results, this is our current confirmed value, but it's like it's completely subject to like how much physical memory is actually there. So yeah, so we could like use this as the number, but then we would basically yeah, not be able to use systems with more memory. Or we could basically choose a random number. And random number, let's say, and so then how do we, I don't know, I'm just gonna kind of walk this through in real time a little bit. So that is the real life numfizz frames currently with the 256 megabytes. And then let's say we, I don't know, we rounded this up. I mean, we can even target certain amounts of like maximum physical memory we want to support. But let me just as an example, let's just say I rounded this up to hex 9000 as the bitmap. Then we're going to do that pre-initialization thing. Below sent a link in the Discord. Let's check that out. How do I get to Discord? Open Discord. Okay, it will be below is sent. I will post it in the chat because apparently I can do that. All right. Elo Belos are to show us all up. Dang. Elo Bilo has this sick physical memory allocator. And using some bitmaps and stuff like this, initializing it, populate free bitmap entries according to the bitmap word. Cool, thanks for the reference. And so let's just say we made it this. And so what we're gonna do next is we're gonna allocate this big bitmap. And then the strategy is going to be to initialize it in place, right? We're gonna go through every single bit and see if it corresponds to a usable page. And if it's usable, we're gonna leave it at 0. And if it is not usable, we're gonna mark it at 1. I'm just also sort of thinking about the case, like what if the free function is accidentally called with a frame that is like not in the usable ranges. Let's say it's a mistake. Is there any way we can assert on that? Maybe might be kind of, it would need to do a lookup, which might be a bit more expensive than we want to do in the deallocation function on every deallocation. I don't know, it's an idea. So anyway, just thinking out loud. Basically, we're going to go through this. So here's the part where now I go back over here and I'm just going to choose a size. So we're going to bring in, let's just try doing this with frig. We're going to bring in the frig bit set and we're going to, I'm just going to give it hex 8000. So this is like, this is like not really an amazing way of doing it, but but that's, let's call this our bit set. And then the thing is, we're going to need to take in the memory map, right? All right, this. So, dang, I'm in German mode right now. It's crazy. Okay, so we're going to include Limine, HPP. Okay. Word. Okay. So got our bitmap allocator, and the thing is, in order to, it depends on the memory map in order to initialize itself. And maybe I'll make this a function, private. Maybe I'll just make this entire thing a class, public, init bit. Call it init bit set and pass in the memory map. Can I? Right. So we're going to call this function from the constructor. And I'm trying not to look at, appreciate you sharing me that code. I'm gonna try to do this on my own and not look at the answer. So we have this bit set, and I guess what's the idea here? We're gonna go through every bit. Bit set dot size. Oops. And what? We need to decide if this is usable or not. And so that's the question, is a given bit usable? And so I'm going to get the fizz, the frame num equals no. Wait, no, yeah, literally the bit index is the frame number. And so bool is frame usable. And we're gonna get a const frame num. Oh wait, oh, you didn't, oh, I thought it was your OS, That's funny. Okay, didn't realize it was Minsky's OS, crazy, okay. So if is frame usable, if is not frame usable, dang, then bit set I, something like this. Am I, shift. All right, how are we looking for every bit in the bit set? We're going to check if it's usable. And you know what, maybe there's a better way to do this. Maybe this is a naive way to do it. Maybe a better way to do it is to loop through every region of the memory map and just do it that way. One stupid way. Loop over every bit and choose. Two, loop over every mem map region and set these in bulk. Question, what about gaps between the regions? Because the regions are not guaranteed. They're like, nothing is guaranteed about the regions actually, so we would need to separately fill in those. That sounds a little bit complicated. So at the start of we would need to track the last frame that we had set, and then on the start of a new region, we would need to see if that region was greater than the last written one, and zero in those bits. What's up, Sweet Coffee? Thank you. And also, hey, Mice too. Cheers. We would need to, keep track of the last set frame on a new region, see if the region is further than the last set frame, and then fill in the distance in between. Track the last written frame, then on every new region need to oh wait, yeah, and right, Illobil, that's what you're saying. You just right, you just zero it out en masse and then selectively reopen it up. That is such a good idea. You're like, yeah, that's totally right. Let's see. I'm pretty sure that should be doable. Dang. Okay. How do I look at where is buffer exposed? You can set flip. Okay, it actually does not look like it. That is interesting. Does bit set. it appears that you're saying it appears that it's indeed, yeah, it is doing that. That's true. Wait, that's yeah. That is true. Okay, so that's what we're gonna do. Okay, let's just go with it. So on construction, it sets them all to 0. So that's what the convention will be. So 0 means taken, 1 is free, and that's just frig, and it's it all to 0 at the start. We want to init everything to taken, and then selectively open up the usable regions. Sick. So let's do that. So, all right, back up here. So what we need to do is we need to go through yeah, all these. You know what I kind of want to do? I want to use a span. Do I have span? I want a contiguous sequence of objects. Constructor. First and count. All right, I don't really know if this is gonna work, but I want to try. So span, and it's gonna be a type Limine entry, mf entry. Extent, or wait, what, span? And let me look at the example. This is not that helpful. Is this gonna work? It's the dynamic extent. And then I need to pass it. Okay, this is falling apart left and right. Span? I do appear to have span. All right, this is kind of depressing. It would be cool to use this. Does Frig have a span? Frig has a span. All right, this is what I'm talking about. Let me try to use a Frig span. So it's going to be so and and we're going to initialize it with a pointer and a size. So it's going to be the memmap.entries. I think that's literally it. And then memmap.entry_count. Does that work? This has a squiggly here, so. Damn, I cannot read German though, so I can't read this compiler message. Wait, but that compiled. Okay, wait, what? No way. Let me break it. Oh, but this is all not used. So I think in order to trigger this, I need to go to k main include frame allocator, and then frame allocator f. What's it called? It's called bitmap allocator. Bitmap allocator. Allocator, right? So now what's up here? There's no, okay, I need to pass in. Okay, this is kind of, I need to pass in this thing. Okay. So let's try that one more time. So now it fails to compile. Warning, warning, the matching constructor. Oh, damn. Okay, so I need to, this is wait, what? Span.hpp. It takes a type name, a pointer to this, and the size n. How is this wrong? Wait, memap dot. Oh, okay, yeah, I need the, I need to, no, I need this, I think. Wait, am I stupid? Memap.entries. No. Wait. It's a pointer to an array of pointers, right? So it's no, wait, so yeah, let me just check this out, I think. So we dereference I've been coding, I've been doing this too long. Okay, that compiles. No, wait, you're saying use the pointer type as a template argument? Oh wait, no, yeah, that's true. Because the container has, that's actually right, that's super right. The container has, yes, it's a container of, yeah, it's a container of pointers. This is, you're totally right. So that's kind of neat, actually. So we can get the span, yeah, whatever. I don't know why std span wasn't working. We can get the span of these things. And then we can do auto, then it's just a bit easier, right? We can, entries. It's just like a little bit nicer. We can then iterate over them with the C++ iterate, like this thing. And we're trying to, if p entry type equals usable. I'm running out of time. And then we need to set all of these range-based for loop. Yeah, exactly. We need to set all of these things to 1 in the bitmap. And so now we need to go through every page in the range. And dang, even 64T cur equals p entry base, but what am I doing? This needs to be in a loop, right? So, but maybe I can also maybe I'll make this a function. I'll just call it init usable region or something like this. Entry. And then I will just call init usable region, and I'll pass in the p entry. Oh, okay, why is this? Dude, I wish I could read that error message. Undo this down these two. Oh, it's not auto. What am I doing? Const entry, right? Okay, so now we can go in here and be like for UN64T cur, or maybe position or whatever, entry dot base cur is less than entry dot yeah, it's totally right, plant hub. Yeah, I just spam const auto everywhere. Or maybe let's go with offset. Let's go with offset 0. As a parameter, I'm pretty sure that's only for lambdas and something like that. Wait, no. And return values? Wait. Holy cooking session. Yo, we are cooking. Yeah, no, this is too much fun and got kind of wrapped up in. I do need to leave pretty soon though, but yo, this is like one of my best streams yet, I think, and I have to thank you all for tuning into it. But we are it's like one of the most, it's like the most I've coded in like almost any stream, I think. I did a lot of coding for JOS, but this is like actually, now this is like finally original code. So, and we're just gonna go offset plus equals hex 1000, and what we need to loop through the region, right? And so basically for this we need to compute the physical frame number, which, so we're just going to do entry.base plus offset. But what is that? That's it's a physical address? Yes, that's a physical address. And so frame num equals p-adder shifted 12. And then bitset dot set frame number. Dang, I think that's now the question is, can you use auto in a function definition? And that does seem to work. I'm actually quite surprised by that, but Elo seems to know C++ very well. Okay, let's put this cur thing offset. I'm still gonna keep it though. So this builds, and this is no longer needed. My alloc function. Yeah, I think, I mean, I didn't even know you could do that, because I mean, I think it can make it difficult to tell what is even being taken. So in C++ that I've seen, we usually don't use it that way. Yeah, no, I think you're right. It's like kind of new, I think. Okay, so let's just recap. So I sort of chose the stupid number as the bitmap size based off of just our experience running things. And this is sort of just like a conservatively high, slightly higher number. This will like break if I increase the physical memory size. We basically will like break and not be able to use more physical memory than this, but I don't really care. And what we're doing is we're just initializing the bit set to only mark the usable regions as free. And to do that, we are looping over the memory map and then checking if we have found a usable region. And then if we have found the usable region, we go through every offset in it, and maybe we can to do assert alignment, and then compute the physical address, and then based on that compute the frame number. And I think that's pretty much it. NSG, personally not a fan of auto. I'd allow it the type name is too long, or variable name indicates what the type is. Yeah, I think it's useful in certain scenarios. I do think it can make the code a little bit harder to read sometimes, but I think overall it makes things a little bit cleaner. Okay, so I think I will inline this. Okay. So we're gonna go with this. And now that we finally have this thing, bitalloc is just like for auto I in M bit set, if I equals 1, which is kind of stupid, but if I wait, no, we want to look for, yes, 1 is an available thing. So if it is available, then why is this not possible? Bro, I cannot read. No, the real reason I have this shit in German is because I'm trying to learn German. So, but no, that cannot be true. They do it right. Oh, they do it in the buffer. So bit set. Is there really no way to iterate over? Do you really need to? Test? I think I need to use a loop. Dang. Okay. Bit set dot size. Okay, then if bit set dot test. This is the part where using libraries kind of, it maybe is even harder than just like raw coding it, because I don't know what test does. All right, we're just going to, it just returns. Yes, so if it tests as true, or you know what, I'm just gonna, can I just do this instead? Personally dislike int, use size t, or fixed with types. Now this is the real debate, which I'm very happy to get into, but not right now because I need to go soon. I don't know. I'm not sure. I feel like signed int is pretty nice because you can assert it that it's not zero, or not negative. I feel like in general, I just default to signed int. I think also the Google style guide bans unsigned int, or bans size. I don't know. I think they ban unsigned int if you can, if you can possibly do that. Like if your code doesn't rely on that. Okay, if this thing, then we're going to go with mbit set dot set I. And we're going to return I shifted over 12. All right, this is all. And then what happens if we do not find anything? We make it optional. How about that? So we return std null opt. Something like this. And then the dealloc will take the phys adder t and then we will, oh shit, set it. Yeah, you're right. Thank you, Illubil, for the good catch. That's confusing me that we've kind of flipped it around. We need to make it 0. So, is it clear? How do you? Flip, reset. Reset. Honestly, I'm not really even sure. This is like, it might just be clearer to do mbit set I equals 0, frankly. Right. So now in the dealloc, using all right. I'm gonna screenshot your comment. You'll be able to remember because I need to get going. But thank you. Yeah, Ariel Guts. I don't have a lot of tools. I mostly just use Miro, this Miro board. And then last thing, so we get the p-adder, and then we get the frame num, which is p-adder 12, and then we do mbit set dot frame num equals 1. I don't know. We could also use the dot set function, but for the moment, I'm finding it a little bit clearer to just directly do this stuff. So that compiles. Did that really compile? Okay, good. So that's legit. Wait. Okay, cool. And now time to, I don't know, like use the allocator. And so for int I equals 0, I is less than, bro, let's like allocate 500 pages or something like that. Okay, that we're going to auto piatter equals allocator dot alloc, and I'm just going to log allocated piatter, and let's just check that out. This will be the last thing we do today. Damn, what the freak? Oh wait, because it's an optional. All right, we're just gonna assert piatter. 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 All right. All right, and here's the part we want to see it shoot past here into this region. So actually, we're going to allocate like, let's allocate 4D or something, or like 4E or something like that. I mean, dude, Bilo, you've been incredibly helpful today, so I really want to thank you for helping me out, really. Also NSG and Ismail and everyone in the chat right now. This has been a super good stream. So we're going to allocate slightly more than what's available in the usable range. And that should pop us over into the next range, and we should observe this. So if I did this right, I'm gonna just make it F. So you know, this is actually not really what is this right? Is this what I'm not actually sure this is what I expected to see. It works. I don't know. Maybe I'm like missing it. I sort of expected this. I expected the number to be like way higher. Like the last 2 pages are in this. Oh wait, true. No, you're right. I was for some reason expecting this. No, check that out. The 1 megabyte mark. Yeah, digitalized. We really locked in on this one. So check it out. It maxed out the first usable region, and then now it's starting to allocate from the second one, and we can see that here. But what is interesting, I think I did the math. I think I did the. I don't know. This like seems a little bit broken. Why is it 9,000? Is that right? Oh wait, true. No, yeah, like because this thing goes all the way up to here, then stops. So that's right. All right. Dang, y'all, this was fun. This was cool. This is like the most code I've written for like the new OS in a stream yet. And we used like a ton of C++ features, which I'm super happy about. We used a class, we used optional, we used a frig bit set, we used a frig span. I'm using const auto everywhere. Yeah, this is like looking pretty good. So that's exciting. And that's where I'm gonna have to leave it off for today. But super fun stuff. Made a ton of progress, and y'all helped me out like a lot today. So I want to thank you all for that. And that'll be it. But we'll be back at it next week and pick off from wherever we want to go from there. So, all right, have a nice week, and I'll catch you next time. Peace, guys. Have a nice one.